Okay, welcome back. This is Calc 1 still, 2.3, evaluating limits, 2.3. So we talked about what limits are and the strict definition of limits. And now we're just going to work with some more general rules of evaluating limits, and particular compositions of things, or sums and differences and quotients of limits. So, for example, there's things you could do with which you can't do with radicals, but you can do with limits. Okay, so the problem I always see with students is, and I teach some pretty basic classes, so I'll see things like this. Students think you take the square root of the individual pieces. The square root of the difference is equal to the square root of the parts, right? No, that's not true. And a good counterexample is always the 25 minus 9, root 25 minus 9 versus, you do it in two different ways. You could see that it's not going to work, right? So square root of 25 minus 9 is square root of 16, which is 4. Of course, if you tried to say that the square root of the difference is equal to the difference of the square roots, that's not going to work, right? Because this will be 5 minus 3, which is 2. So this second version is bad news. It's a big no. It turns out though, with limits, you can pull this kind of trick. So you'll be happy to know that it's a little easier in that respect. Okay, you can pull these things apart. Okay, so anyways, I'll go through the properties of limits, and the way I want to do it is just to, rather than writing out the properties, which you could read in your book, I'm going to do examples of the properties. Okay, so I'll, of course, reference which theorem these are labeled in the book. This is first theorem 2.1, and of course there's 3 rules here. Basically, the limit of a constant is equal to the constant. So the limit as x goes to 3 of 7, for instance, that's just going to be 7. And visually, what you think of is kind of, you're looking at the line y equals 7, right? So 1, 2, 3, 4, 5, 6, 7. And then you want to know what happens as x approaches, what happens to the y value as x approaches 3, right? So what's happening to the y value? Well, the y value is always 7, so no matter where you put it, if you want to know the limit as x approaches negative 100 of 7, you're always going to end up with 7, okay? Okay, so simple enough. The second one, then, the limit as x approaches 7 of x. In this case, it's just plug and chug, right? So it's literally y equals x is this diagonal, and then as we approach 7, the y value will also be at 7. Okay, so this point is always just x comma x. Whatever the x value approaches, that's what the y value approaches. So, but you could do a substitution. You can literally just put the 7 into for x, and you end up with 7. Another example, what's the limit as x goes to negative 3 of x? And then you could just put negative 3 in for x, and your limit is negative 3. Okay? Okay. Then if you have these things exponentiated, so the limit as x goes to, let's say, 2 of x to the whatever power you want, all you need to do is plug 2 in for x, and then do the power, and you get your answer. So 2 in for x is 2 to the 4th then, and your answer, 2 times 4, 8, 16, right? Okay, and that'll work with any power that you deal with. Okay, so that's the first theorem, and then we kind of build off of this theorem to get these other rules. And you could prove, I believe you could prove all these rules using delta epsilon proofs, which you would do if you took more advanced calculus. We won't bother with. Okay. So anyways, theorem 2.2, and for me to give you um, some interesting examples, I need to have you let um, the limit as x goes to pi of sine of x. And we haven't talked about limits of trigonometric functions, but it'll turn out that all you have to do here is a substitution as well. Um, when you do substitutions, that's kind of a special function. If the limit of the function as you approach some number is equal to the function evaluated at that number, it's considered continuous. We'll learn that later on. So these, when you have a substitution, when you have a limit that's just as easy as doing a substitution, it means something. Okay. Anyways, the limit as the of sine of x as x goes to pi, just put pi into there, and you get sine of pi. And the sine of pi then is just 0. Okay, so let that equal that, and then also let the limit as x goes to pi of cosine this time of x. That'll equal cosine of pi. I'm running out of room here, but cosine of pi is just -1. Okay. All right. So we want to go through this next set of theorems using these examples. So the first example, you can always multiply a function by a constant, and it won't really kind of affect the limit. It's okay. So let me just show you. So the limit of 5 times cosine of x. Okay, all you have to do is literally just put pi in for cosine of x, and then your answer is going to be 5 times the -1 that you got here. You could think of it as kind of factoring the 5 out of the limit, like this. And you get cosine of x. And then you just have 5 times this thing, which we have up here, which is -1. So you get -5. Okay, so constants can be pulled out of limits, I guess is one way to think of this rule. Secondly, then the limit as x goes to pi of the sum or difference of these two things. Okay. And this is kind of what I was talking about with the roots. Let's say minus cosine of x. The limit of a sum is equal to the sum of the limits, so long as the limits exist. Okay, if they don't exist, then you got a different kind of problem. But if we have this assumption that we kind of know what these limits go to, and this is probably one of the drawbacks of me using examples rather than just writing out the properties, you have to have that these limits go to something. Okay, so the limit as sine of x as x goes to pi, we know equals something, and you know, so long as that works, you can break them apart. Okay. Then you have 0 minus -1, which of course is +1. Okay. So the limit of the difference in this case is equal to the difference of the limits. 3, you can also break up products, presuming that the individual limits have limits, or the individual functions at that point have a limit. So here we have limit of sine x times cosine x. You can rewrite as the limit as x goes to pi of sine x times the limit as x goes to pi of cosine x. So when you put in pi, you'll get 0 times -1, which will be, of course, just 0. But if you look back here, I mean, that's the exact same thing you would get if you put the pi into these guys and then just multiply it out. And, you know, that's generally what you'll do. You won't worry about breaking these apart. It's only when you're having trouble evaluating the limit that you'll really go through these extra steps. Anyways, let's look at the quotient now. The limit as x goes to pi of sine x all over cosine x. And this is equal to the limit of the quotient of the limits, right? So the limit of sine x all over the limit of cosine x. In this case, the limit of sine x is 0, cosine x is -1, so that's just 0. If the denominator was 0 instead, so if I had the limit of cosine over sine, we would have a different kind of issue. That would be one of those unbounded cases, right? And you'd have probably take a look at the graph or do some sort of numerical analysis to figure out which way it's going, right? It's probably the limit just doesn't exist. So it would go to infinity in one direction, negative infinity in the other. Anyways, let's look at number 5, where again we have these exponents, and you can kind of move the limit inside the exponent. So let's say cosine of x to the 25th, right? You can kind of slip the limit into these parentheses and just consider the limit as x goes to pi of cosine of x, and then raise that result to the 25th power. Okay, so the limit as x goes to pi of 25, as x goes to pi of cosine x, of course, is -1, and then -1 to the 25th to an odd power. That's just -1 again. Okay, the next is about the limit of polynomials. Basically, it's kind of like these rules on steroids. So if you continuously kind of compound these rules, you'll find in general for any polynomial, you can go ahead and just do a substitution, right? So in particular then, this is theorem 2.3. And it's about polynomials in general. I'll just give you an example though. So the limit as x goes to 2 of x cubed minus 2x squared plus x minus 3. And you could do a substitution on polynomials. It's going to work. You could break it all up, obviously, and take the sum of the limits, and then you could factor out these constants. But at the end of the day, theorem 2.3 is telling you could just do a substitution. Okay, so you get 2 cubed minus 2 times 2 squared plus 2 minus 3. Okay. 8 minus 8 is 0. 2 minus 3 is -1. Okay. You can also do this with rationals, so long as the denominator is not 0. Okay, so for instance, if we have the limit as x goes to 2 of maybe this guy, x cubed minus 2x squared plus x minus 3, all over, let's say, x squared minus x plus 1, then I could do a straight sub, so long as this guy is not equal to 0 at 2. Okay, so maybe we could call that polynomial q of x, and we know q of 2 is not 0, so therefore we could do a straight substitution. The numerator is -1 from before. The denominator 4 minus 2 is 2, plus 1 is 3. So our limit is -1/3. Theorem 2.4 then is on radicals. So first off, we have the limit as x goes to 16 of this 4th root of x, and this will be true for any particular root that we care about. Obviously, it has to be approaching something in the domain of x, and if it's at 0, we have to consider the right-hand approach, right? So from the left, its limit won't exist because it will be undefined. So anyways, you could do, again, it's just a matter of subbing this into here. So you'll just have the 4th root of 16, which is 2. Okay. So get theorem 2.5. So this is done on composing functions. And it seems so long as the outer function is defined at the place where the inner function is going to, you have a limit. You can just do a straight substitution again. So first, let's consider the limit as x goes to pi of 3x. And of course, via substitution, we can just say that's 3 times pi. And then limit as x goes to 3 pi, which is where this guy's going. And in other words, the outer part of my function, which I'm going to define here in a second, is defined at the place where this is going. If that's all true, then we can do a composition of cosine of 3x, okay, and then consider where the limit goes as x goes to pi, right? So the cosine of it's this function of this function. Okay, so I'm putting this into here, and then I'm taking the limit as x goes to pi. If this function, the cosine, is defined at 3 pi, which it is, then I can literally just move the limit inside of the function like that and take the limit of 3x, and I'll get, of course, cosine of 3 pi, which is equal to -1. Okay? So you can kind of do a lot with these limits, just blindly kind of moving them around. You can move them in, you can break them up. You want to be a little bit careful. You have to make sure the bits and pieces are defined. Okay, if they're not, then you really can't pull this off. But so if you have like a nicely behaved guy like these guys that are continuous, and then these guys that are continuous everywhere except where, for instance, the denominator is 0, you always just do plug and chugs on these cases. Okay, I don't know. So it's when you get the more complicated cases, you're probably going to have to default back to these theorems and see what you can do. Anyways, let's now look at the transcendentals. I've kind of already talked about the transcendentals. You could just do plug and chugs like the polynomials, so long as they're continuous. So cosine and sine, you're good to go there. But other ones like tangent, you may have to be a little more careful because it does have discontinuities. Okay, so transcendental functions. This is example 5 from the book this time, part A. The limit as x goes to 0 of tan of x. Okay, so tan is defined at 0, so there's no issues with asymptotes or unbounded behavior. So we can put 0 directly in the tan, and of course that's equal to 0. The tan of 0 is 0. Let's look at the limit as x goes to 0 of sine squared x. Some reason our brains have a little trouble processing this squared thing. It's really sine in parentheses squared, right? And it will turn out that we can go ahead and move the limit inside that square. So it's sine x squared. And then you can move the limit inside the parentheses. So we'll have the limit of sine x as x goes to 0, and then square the result. So that'll just be 0 squared, which is 0. Okay, some other characters, exponentials and logs. You can do plug and chugs. So the limit as x goes to -1 of x e to the x. Okay. Each individual limit has a result. So the limit as x goes to -1 of x is just -1. And then the limit as x goes to -1 of e to the x is e to the -1. So we can, the limit of the product is the product of limits. And ultimately, it's just a plug and chug. If you had just substituted here, you'd get the right answer. Okay, so anyways, it would be -1 times e to the -1, which is -1 all over e. Let's skip ahead to theorem 2.9, I guess. And these are some special trig limits that were expected, at least in the beginning, to kind of have memorized. It turns out that we'll have methods later on, L'Hopital's method, that will allow us to kind of forget about these rules. But the book uses it basically to introduce the squeeze theorem. Okay, so the limit as x goes to 0, sine of x over x is 1. And there's geometric proofs for these things that exist out there. I'll kind of show you the one that's in the book. If you go online, though, and watch videos of calc classes from other schools, they'll have more stuff for you. limit as x goes to 0, 1 plus x to the 1 over x is equal to e. So these are sort of standard limits. You'll use them in the exercises to evaluate limits. But the first limit we take a closer look at, and we use it to kind of introduce this thing called the squeeze theorem. So theorem, and I'll introduce the squeeze theorem, and then we'll prove this, right? So theorem 2.8 is the squeeze theorem. And it's pretty intuitive, I think. If h of x, some function h of x is less than or equal to f of x, which is less than or equal to g of x, and probably some sort of interval, and we know that the limit of this guy and this guy equal the same thing, it forces the limit of this guy to equal that. So if we have the limit of h of x equaling some number L, which equals the limit of g of x, then we can conclude that the limit of f of x is equal to that same thing. Okay, and of course in the book there's restrictions, and you should go read that. But this is the flavor of the theorem that we should try to digest. Okay, so let's go back to theorem 2.9 and try see if we can prove this in sort of this geometrical fashion. So this is from theorem 2.9 again, and we want to prove that one particular limit, the limit, and we'll use angles instead of x's. So sine of theta over theta as theta goes to 0 equals 1. Note, if you would just plug theta in for 0 in for theta, you wouldn't have been able to evaluate that because its form is what they call indeterminate. So if sine of 0 is 0, and then if you plug 0 in for theta, you get 0. So 0 over 0, we're not exactly sure what that does. And you want to think of it as kind of a competition to be determined. All right. So we're going to attack this geometrically, and we're going to dive into the unit circle that you're probably familiar with from trig, and then make some inequalities out of it, and then we'll be able to manipulate the inequalities in a way that will allow us to take advantage of the squeeze theorem. Okay, so what we'll do here is build a triangle in the first quadrant like this, and then we want to kind of note some of the different points on this triangle. So this is the unit circle, of course. That means the radius of the circle is 1. So in particular, we know this point is going to be, well, what? It's 1, 0, right? And then we're going to put these other points kind of in terms of cosines and sines of theta. So we'll presume that this angle here is theta. All right, so this point right here is going to be cosine theta comma sine theta. This point right here at the top of the triangle, if you remember, tan of theta is going to equal opposite over hypotenuse. So if this point is just plain old x comma y, some generic point, we know that the x-coordinate from this point is 1. Okay, so the x-coordinate is 1. And then the y-coordinate from ratios of side of a triangle, you know, opposite over 1, if this is y, then this thing is just plain old y, but y is tan of theta. So note, tan of theta is equal to opposite over hypotenuse. So opposite all over, and then I think I just ran into a problem. It's opposite over adjacent. So it's, sorry. Yeah, so tan of theta is equal to y. It's this distance here, so we can write this coordinate as 1 comma tan theta. Okay, sorry, I hope I didn't butcher that too much. All right, so now we're going to form our inequality based off these kind of diagrams. I'll start with the whole triangle. Okay, so I'm going to consider the areas of this from this figure here. Okay, so here I have the whole triangle. What's the area of that whole triangle? So the area is equal to 1/2 base. The base is 1, and then times the height. And the height is y, but we're going to say that's tan theta. Okay, so 1/2 tan theta. And then getting a smaller triangle, we can consider actually a sector of the circle. So we extract this smaller portion. Okay, so the old triangles, it's embedded in that triangle that we worry about. It's right there. Okay, and the area of that is from the area of a sector of a circle. So the area will be, what is it, 1/2 r squared theta. So in this case, the radius is 1, so it's just 1/2 theta. Okay. And then finally, we're going to take an even smaller portion than this portion here. And of course, the old triangle is sitting right here, and then the sector would have been there. The area of that portion, 1/2 base, which is 1, times the height, which is given by this coordinate here. So the height would be the y coordinate of this point, which is sine theta. So it'd be 1/2 sine theta. Then we notice the relationship between these three areas. Well, obviously this area has to be greater than or equal to this area, which has to be greater than or equal to that area. So we formed an inequality, and we want to apply the squeeze theorem eventually. I still need to kind of back engineer this expression. So how am I going to do that? Well, I'm going to first divide through by sine. Tan is sine over cosine, so I'll be left with the 1/2, of course, and then times cosine of theta. That'll be greater than or equal to 1/2 times theta all over sine theta, and then that's greater than or equal to just plain old 1/2. Okay. You know, multiply through by 2 to get rid of the fractions, and then we're going to just take reciprocals through, and that will change the direction of the inequalities. Okay, so I'll end up with 1 less than or equal to sine of theta over theta, and that'll be less than or equal to cosine of theta. Okay, finally we got the expression from the limit we were after. We also have it wedged in between these two functions such that we could take the limit of these two things. So I note that the limit of 1 as theta goes to 0, that's just the limit of a constant, so you'll get 1. And then the limit as theta goes to 0, cosine of theta, the other side, well, that's just 1 as well. So that forces the middle guy to be 1 as well. So the limit as theta goes to 0 of sine of theta all over theta is equal to 1 by the squeeze theorem. Okay. Okay, so the squeeze theorem, you'll use it every once in a while, not very much. It'll come up later in Calc 2 when you're dealing with sequences. So it's not something that'll go away, but it's something that you don't use every day. Right? It's only when you're in a pinch you'll sort of use it. Okay. Okay. So, anyways, let's just look at some problems from the book. We'll look at kind of what are the problems based off this theorem, and then we'll hook back around and take a look at some regular substitution kind of problems, and then we'll look at some indeterminate forms. Right? Okay, so here let's look at 67. This is a limit as x goes to 0 of sine of x all over 5x. Okay, so you need to get it in the form from the book for these limits to pan out. So I need something sine of something all over that same something. So you can factor out a 1/5 here, and then it becomes obvious that you're dealing with our friend sine of x over x, which is 1. Okay, so we'll have 1/5 times 1, which is 1/5. Here's 79. This one's a little trickier. we have sine of 3t all over 2t. Again, we need to get the angle here and the angle here to be the same. So I want 3t and then 3t down here. So you're going to have to do some clever arithmetic as the gateway. So the gateway to solving this problem is arithmetic. How does that work? Well, you want to kind of clear out the denominator by multiplying by 2. But if you multiply by 2, you have to immediately divide by 2. Then we also want to put a 3 in the denominator. So I multiply by 1/3, but if you multiply by 1/3, you have to multiply by 3. Okay? And then times the sine of 3t all over 2t. Okay, so this 2 will cancel with this 2. And then we're going to factor out this part of it. Okay? And that'll leave us with sine of 3t over 3t. So I factor out the 3/2, and I got the limit of sine of 3t all over 3t, which is now in the form that we want. We can now apply the theorem. This is 3/2 times 1, which is just 3/2. Let's look at one with cosine in it. So this is 73. I'm taking a look at the limit as h goes to 0, 1 minus cosine of h squared all over h. Okay, so the original theorem, if we look back in our notes, doesn't have that squared thing in here. But if I can factor it, and then I can take advantage of the fact that the limit of the product is the product of the limits, assuming that those limits exist, then we're in good shape. So let's try that. Limit as h goes to 0. 1 minus cosine h squared is same as 1 minus cosine h times 1 minus cosine h, right? So I could rewrite this expression as this. And note, if you multiplied it back out, you would get back here. Well, why would I want to do that? It's because I know the limit of this thing. And if you look at this, plug in 0 for cosine, you would get cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. 0 over 1 is 0. So I know this part too. So if you know this and you know this, then you could take the limit of this times the limit of this, and you have your answer. Okay, so that'll equal the limit of 1 minus cosine of h over h times the limit of 1 minus cosine of h as h goes to 0. And of course, this guy is just 0, and then times this guy, which also, I guess, turns into 0, right? Cosine of 0 is 1, 1 minus, yeah, okay. So 0 times 0 is 0. Okay, let's circle back around and just look at some of the simpler limits from the book. Here I have the limit as x goes to 2 of x cubed. This is a polynomial. It just has one term. It's cubic. And therefore, by our previous theorem on polynomials, we just do a substitution. In fact, I think most of these, you could probably just plug and chug and say it's a good day. All right? So 2x minus 1, if you plug 0, this is another polynomial, you could just plug and chug. 2 times 0 is 0, minus 1 is minus 1. It's 9. The limit of 2x squared plus 4x plus 1, another polynomial, just go ahead and plug and chug. This will be 2 times 9 minus 12 plus 1, 18 minus 12, 6, 6 plus 1 is 7. Technical difficulties there. Number 11, we have a radical. And then inside the radical, we have a sum. Okay. All right, so we can move the limit inside, so to speak, and we'll have 3 plus 1 is 4, and then the square root of 4 is just 2. So we have the limit as x goes to 7 of 3x all over the square root of x plus 2. And again, you could just plug and chug so long as the denominator is not 0. And this value's in the domain of this expression will be good. And that's true. So here I have 3 times 7 is 21, all over 7 plus the square root of 7 plus 2. This is the square root of 9. So it's 3. That'll give us 7. Okay, great. So it's obviously not going to always be that easy. And of course, we see in example 6 that substitutions do sometimes fail. So section 3, failure. So example 6, we have the limit as x goes to 1 of x cubed minus 1 all over x minus 1. So this is a rational function. We have a ratio. So long as the denominator does not end up equaling 0, we can just do a substitution. And here, the denominator does not equal 0. But on top of that, if you plug 1 into the numerator, you also get a 0. Okay? So this is special. If you had like a number in the numerator like 5 all over 0, it would be unbounded. Okay? But this one is called indeterminate. So if you have 0 over 0 form, this is a special kind of form, indeterminate. Okay? You'll study those more extensively in Calc 2. Here we give you some algebraic workarounds. Okay, so we note for all x not equal to 1, we can reduce this expression algebraically. So x cubed minus 1 all over x minus 1, we note this. This will equal to, well, this is a difference of cubes, so I'll have x minus 1. It's a slope formula. Same, opposite, always positive. We have x squared plus x plus 1 all over x minus 1. And for all x not equal to 1, we can remove those guys and just be left with x squared plus x plus 1. So this limit back here, and we can only do this because of a theorem, hence by theorem 2.7, the limit, the original limit that we were working with, limit as x goes to 1 of x cubed minus 1 over x minus 1, will equal just the limit of this thing. Okay? Limit as x goes to 1 of x squared plus x plus 1. Okay, and then that's just a plug and chug, because that's a polynomial. We can do substitution. So that would be 1 plus 1 plus 1, which is 3. Okay, so the deal is, in general, you want to kind of try to start with a sub. So we kind of have a strategy coming out of it, or a program, so to speak, strategy. First, always try substitution. Try substitution. Then if your substitution doesn't work, so it's resulting in something like a 0 over 0, do some algebra. So if your sub fails, do algebra. And then, there's other things you could do. You could look to the graph. Go and look at what your computer software is saying if you have that handy. So basically just look to your computers for the answer. All right, so let's take a look at the algebra ones that we can handle algebraically. Here's 55. It's the limit as x goes to -3 of x squared plus x minus 6 all over x squared minus 9. Okay, so you try a substitution. You try to plug -3 into here. You get 9 minus 3, which is 6, and then 6 minus 6 is 0. I'll just sort of notate that there, or record it. Then if you put -3 in the denominator, -3 squared is 9. 9 minus 9 is 0 again. So yeah, we have an indeterminate form. So we're going to have to do something special. And the only thing we really know how to do special at this point is to reduce the expression. So you try to factor it. X squared plus x minus 6 is the same as x plus 3 times x minus 2. And then the denominator, that's a difference of squares, so that'd be x plus 3 times x minus 3. Then we can simplify. And so for all numbers not equal to -3, and of course when we're dealing with limits, we don't really care about what happens exactly at that point. We're just worried about approaches. Anyways, we have x minus 2 over x minus 3, and now you could do a plug and chug because it won't be an indeterminate form. So -3 minus 2 is -5. -3 minus 3 is -6. So our limit is 5/6. Let's do just one more. And this is the limit as x goes to 3 of the square root of x plus 1 minus 2 all over x minus 3. Right. So for this guy, what you're going to need to do is, well, obviously check the form. Maybe you can do a plug and chug, right? So it'll be square root of 3 plus 1. Square root of 3 plus 1 is the same as square root of 4. Square root of 4 is 2. And then 2 minus 2 is 0. Downstairs, 3 minus 3 is 0. Oh, so it's indeterminate again. We got to do something clever, or we have to open the gateway with some sort of algebraic method. We don't really know anything else. So what it will come down to is rationalizing the numerator. Okay, so you may have seen this before. Sorry. So I have the square root of x plus 1 minus 2 all over x minus 3. It's the same as rationalizing the denominator, except you take the conjugate, multiply top and bottom by the conjugate of the numerator. Right? So I'm going to multiply top and bottom by x plus 1 plus 2. You just change the sign of the sign in between these two expressions, all over the square root of x plus 1 plus 2. Okay? So this will equal then the limit as x goes to 3 of, and I want to FOIL these guys out. So x plus 1 squared times x plus 1, the square root of x plus 1 times the square root of x plus 1. The square roots go away, I got x plus 1. The inner and outer terms will add to 0, and then the last term's -4. Downstairs, I'm not going to multiply that out, and you'll see why here in a second. Okay, so simplify the top and see what you get. Oh, that's why you didn't want to multiply it out, right? So nice little cancellation there. The x minus 3's go away. And then you're going to have to check by substitution again and see if you are good to go. So I have square root of x plus 1 plus 2. And sure enough, I have an answer. It'll be 1 all over square root of 3 plus 1 is square root of 4. Square root of 4 is 2. 2 plus 2 is 4. So the limit is 1/4. Okay, thanks for watching.